Welcome back to the Deep Dive. Today we're getting into something pretty fundamental, an idea that really shook up physics and even nabbed a Nobel Prize. We're talking about Bell's theorem, quantum mechanics and hidden variables.
Yes, right.
Our mission, really, is to unpack this core puzzle. John Bell tackled, the old debate kicked off by Einstein, asking, is quantum mechanics the whole story? Or is there something else, maybe some hidden stuff, pulling the strings? We've got a fantastic expert with us today to help guide us through.
Happy to be here. Yeah, for decades, physicists, they really struggled with this. Could there be these unseen, these hidden variables that would make quantum mechanics look more, well, classical, deterministic?
Like making things predictable again.
Exactly. Do particles have definite properties before we measure them? That was the core of the EPR paradox. It questioned if quantum mechanics was complete or if this spooky action at a distance was just weird.
Right, spooky action. So fast forward to 1964. John Stuart Bell comes along with this paper. And it wasn't just philosophical anymore, was it? He gave us a way to actually test it.
Precisely. A mathematical framework.
Okay. But before we dive into the test itself, let's quickly nail down these key terms. Local and hidden variables. What do we mean by locality?
Locality is basically the common sense idea that things are only affected by their immediate surroundings. Nothing travels faster than light to influence something else instantly far away.
Makes sense. No instantaneous spooky messages across the galaxy.
Right. And hidden variables, those are the hypothetical things, the properties we maybe can't see, that would predetermine the outcome of a quantum measurement before it happens.
So they sort of fill in the gaps Einstein was worried about.
That was the hope, yes, to restore that classical sense of reality.
Okay. So what Bell did was, what was so clever about his approach?
Well, what's really fascinating is how elegant it was. He showed mathematically that if the universe worked according to local hidden variables, there's a strict limit, a ceiling, on how strongly correlated measurements on entangled particles could be.
A limit.
A limit. We call it a Bell inequality. But here's the kicker. Quantum mechanics predicts correlations that break that limit. They go beyond what classical physics with local hidden variables would allow.
So there's the conflict.
Exactly.
Yeah.
Bell himself said, basically, if a theory is local, it won't match quantum mechanics. If it matches quantum mechanics, it can't be local. You have to choose.
Okay, let's try and make that concrete. You mentioned entangled particles. So imagine Alice and Bob. They're really far apart, okay? And they each get one particle from an entangled pair sent by Victor. They each randomly choose one of two measurements to make. Now, if local hidden variables were running the show, then the average result, how correlated their measurements are, would have to stay below a certain number. Like in the CHSH version of the inequality, that number is 2. It can't go higher. Right, classically limited to 2. But quantum mechanics says.
Quantum mechanics predicts correlations for entangled particles can go higher, up to about 2.828, actually, 2 times the square root of 2.
Wow, okay. Significantly higher. And this isn't just math on a blackboard, right? People tested this.
Oh, absolutely. That's the crucial part. Starting back in 1972 with John Clauser and Stuart Friedman, then Elaine Aspect did more refined tests in the 80s.
Right.
And more recently, around 2015, we got these incredible loophole-free experiments. And the results, they consistently violate the Bell inequality. They match quantum mechanics, not the local hidden variable predictions.
So reality is weirder than the classical picture.
It seems so. Local hidden variables, as originally conceived, just don't match what we observe. And that work, confirming this, is what led to the 2022 Nobel Prize for Clauser, Aspect, and Anton Zeilinger.
Okay, so the experiments basically slammed the door on local hidden variables. What does that actually mean for us? For how we understand reality? That sounds pretty huge.
It is huge. It means our everyday intuition about how the world works, objects having definite properties, only local influences that intuition breaks down at the quantum level. We're forced into some uncomfortable choices.
Like what? What are the options if local hidden variables are out?
Well, different interpretations of quantum mechanics take different paths. Some give up on realism, the idea that properties exist before measurement. Maybe the measurement itself creates the outcome.
Okay.
Others accept non-locality. Theories like Bohmian mechanics propose hidden variables, but they're non-local. Particles can influence each other instantly, faster than light. That spooky action is real.
Wow.
And then there's a more fringe idea called superdeterminism. It suggests maybe the hidden variables and the experimenter's choice of measurement aren't independent, which gets really weird, questioning free will itself.
So superdeterminism is like everything was set up from the Big Bang, including which measurement Alice would choose.
Sort of, yes. It avoids non-locality, but at a potentially high philosophical cost.
Right. So wrapping this up, Bell's theorem isn't just some abstract equation. It's telling us something profound about reality itself. That spooky action Einstein worried about. It seems to be baked in.
It forces a choice, really. Either you accept the inherent strangeness of quantum mechanics, its non-locality, or you have to abandon other fundamental ideas we take for granted, like locality or perhaps even the independence of observers.
It leaves you thinking. Maybe the universe isn't just stranger than we think, but like fundamentally stranger than we can intuitively grasp. Reality woven from threads we're barely starting to see.
That's a good way to put it. It certainly keeps physicists busy.
Definitely something to ponder. Thanks for joining us on The Deep Dive.